Hi everyone, this is Stefano Marani. I am Chief Executive Officer of Renogen, a dual-listed company on both the JSE and the ASX. We're an emerging natural gas and helium producer with an operation in South Africa, which we refer to as the Virginia Gas Project. In light of the increased interest from the general public with regards to helium and what it's used for, and the economics surrounding it, it prompted me to create this podcast, which I'm cheekily calling Helionomics. And hopefully by the end of it, you can all call yourselves heliumologists if you watch this through to the end. This podcast is in no way meant to be any form of forecast of Renogen in any way, shape, or form. This is literally just a helium 101 on the market and how it works. So I'm going to turn on my whiteboard and I'm going to draw a whole bunch of pictures. But I would highly recommend, I am on LinkedIn, I am on Twitter, and for all of those of you on Hot Copper, I do read those comments. So a shout out to guys like Taz Devil and Sir Dad and Thaddeus and Goldbug Bob and Iron Mike. I'm reading all of your comments. I'm seeing those questions, and so to that end, when I do get a chance, I do put little videos like this together to try and answer those questions. But by all means, I am on LinkedIn, I am on Twitter, and I am available. So so ask your questions to me directly as well if you want. Let me get a whiteboard up here so that I can start drawing. All right, so firstly, the nomenclature regarding helium. There's a lot of confusion as to kilograms versus MCF versus BCF, and to be honest, no one really knows which one to use. So the difficulty over here, and certainly the challenge that we had when we came into the helium market for the first time, was trying to get to grips with all of the different nuances. And I get the sense that the majors deliberately make the market as complex as possible so that no one can really know what they're talking about, other than the majors themselves. So hopefully this will dispel some of that. You get helium is sold in two basic primary units, either in cubic feet or in kilograms. Now, what's important is to understand the ratio between these. So when you have 113 cubic feet, you have 1 kilogram, and this is the all-important ratio. Alternatively, assuming that you have 1,000 cubic feet, you would have approximately 4.7 kilograms. Those are the magic numbers that you need to know. Now, the minute that you have 1,000, that is little MCF. Of course, for some bizarre reason, when you talk about million as opposed to 1,000, then the little m becomes capital M. But I'm told that that only represents money, so dollars. So you can't use the capital M for volumes. So it all starts to get a little bit confusing, especially when you then consider that B is only used in capital and not in lowercase. So yeah, to be honest, it's just easier when you talk about either the unit of MCF by itself. Sometimes they use MMCF, but if it's all lowercase, then you know that that is 1,000 or a million cubic feet. But for the purposes of this, we're either going to be talking in MCF, and each one MCF is equal to 4.7 kilograms, or we will talk in 1 kilogram, which is equal to 213 cubic feet. These are the all-important numbers. Now, helium is pretty much like any other commodity. Let's say, for instance, that you are looking at a gold mining prospect. If you are busy extracting ore out of the ground, then the gold in the ore will have a certain price. If you then extract that gold from the ore and you begin to refine it, once you've turned it into 99.99% pure gold, the value of the gold per ounce is worth a lot more than the value of the gold per ounce still in ore form. And this is logical because you spent a lot of money refining it. And then if you take that pure high grade gold and you then turn it into jewelry, then per ounce it's even more expensive than it was in bullion. This is no different to helium. Helium, obviously, when it's sitting underground at low concentrations, has a value. When it comes up to the surface, and you purify it to call it anywhere from the 97% all the way up to 99.9%, this is low-grade helium. This is not capable of being liquefied. This goes to the gaseous market. So the gaseous market would typically be your balloons. It would be some applications in welding, and it would be a very localized market. In other words, it's not going to transport very far. And the reason that it doesn't transport very far is because you can't liquefy it. So you've got to put it into a giant steel trailer that weighs about 26 tons. And in that, you're only moving, maybe a few hundred kilograms of helium. And that means that your transport cost is absolutely gargantuan. So this is a very specialist type of market. It's typically highly saturated because there is a lot of gas available. And the reason that there's so much gas available is quite simple. Helium, when it's transported cross-border and overseas, it gets transported in an isotainer. When the isotainer leaves the refinery, it's liquid to a purity of what we call 5 nines. That's 5-9. Obviously 4-9, you drop one of the nines, but that's how they define the grade. Every single day that the trailer is in transit, about 1% of the total volume over here converts into gas. And that means that you increase the pressure in the trailer. On the 45th day, the pressure over here is so high that the trailer has to be vented in order to try and accommodate the pressure without damaging the trailer. By the time that the trailer gets to the customer, the gas on the top needs to be taken out to protect the trailer. That then goes into compressed cylinders. And those compressed cylinders then go off and get sold as compressed helium to their customers at the end. And that is pretty much why there is a massive glut of gaseous helium in the market. And that is literally just because there is all of this boil off over here that is very, very difficult to contend with. You then move into the next grade of helium. You get to 4 nines. At 4 nines, this is where you have the ability to now start liquefying your helium. And yes, you can liquefy it at lower grades, but what you need to appreciate is that carbon dioxide solidifies at about minus 120 Celsius, roughly. LNG liquefies at minus 162 degrees Celsius. Nitrogen liquefies at just under 200, somewhere around plus minus. Liquid helium, you're talking about minus 269 degrees Celsius. That is a very, very, very low temperature. That means that if you have any impurities, those impurities have turned into icicles. And typically what will happen is that you will then have these little ice particles floating around in the machine, in your helium liquefier, while the helium is actually still in gaseous form. And these little ice particles then get trapped inside your machinery and they break. And what kind of machinery are we talking about? We're talking about a tiny little turbine that's about the size of my pinky nail. It spins at 3,200 revolutions per second, not per minute, per second. It spins so fast that it has to levitate on a bed of pressurized helium as opposed to a ball bearing, because you can't have metal on metal contact. Now that little thing expands the helium to the point where it's almost at liquid form. If you're going to have something that is literally the size of my pinky nail, spinning at 3,200 revolutions per second, and you have a little piece of ice get into that, it's going to damage your entire liquefier. So really, this is the threshold at which point, if you want to run a long-term plant, that's where you start liquefying it at. But over a long period of time, if you're liquefying helium at that purity, you're still going to end up with problems. So ideally, what you want is that you want to get to 99.999% purity, because then you will have a long life of plant. So this is really the market that you want to play in. This is where the valuable stuff is. The rest of it, supply and demand varies, and the pricing varies. All right, so when it comes to construction timelines for these plants, the gaseous helium is quite easy. You've got your wellhead, and that wellhead then feeds gas into the membrane, and that membrane will then separate out all of your other gas. We'll just refer to that as other, and then you'll end up with helium, and that helium will be anywhere up to, call it 97-98% purity. That's quite easy, because then all that happens over there is that goes into a compressor, and then you can stick that into your trailer, and your trailer then goes and takes it off to the market, and happy days, you're selling gaseous helium in a very nearby vicinity, and you haven't spent too much money in terms of refining. A plant like this you can probably build in, say, 6 months to a year, depending on the timeline that it takes in order to procure the membrane. That's probably the most complex thing in this operation, and I'm obviously skipping out large parts of engineering, but this is basically the secret sauce when you're talking about gaseous helium. The minute that you start talking about liquid helium, your wellhead then feeds a series of compressors, many compressors. And what these compressors then do is that they then help you get your gas. First box kicks out CO2 and hydrogen sulfide. Then your second box is going to kick out your LNG. At this point, you now have helium and nitrogen at a temperature of about call it minus 160 to 170. It then gets into your helium liquefier. This is quite a complex process. To put it in context, the amount of energy consumed over here for your tiny little stream of gas coming in almost exceeds the amount of energy that you use to get the rest of the product done. So in a nutshell, the reason that liquid helium is so expensive is very simply because there's an enormous amount of electricity that goes into turning helium into a liquid. So without going into the exact specifics of how a helium liquefier works, it's a really interesting process. It's just constant expansion and contraction using the Joule-Thomson effect. And every time that you expand it, you cool it down. When you compress it, you heat it up. Then you throw liquid nitrogen over the heated up mess. And you keep doing that until you eventually get it to the point where it's highly compressed and it's at minus 255, say. Then it's just a kind of a sludgy plasma. It's neither liquid nor solid. And then you put it through some valves, and it magically turns into liquid. So that's roughly the process. But I think the key takeaway from this is that if you're going to produce liquid, you're going to use an inordinate amount of electricity. So to put some rough numbers to it, our project, we're looking at around 350 kilograms per day. Why is my stylus not writing? 350 kilograms per day. That, to put into context, is obviously plus minus, roughly speaking, about 75,000, or at least it's 75 MCF per day. See how easy it is to get the numbers wrong. It's approximately equal to 350 kilograms. The amount of power that we're estimating that will go into the production of that is, give or take, 1 megawatt of electricity continuously for 24 hours, which is a huge amount of electricity for a very small amount of helium. So that gives you an idea of the kind of electrical efficiency that you need in order to get it down. Now, this takes into account the fact that when the helium is getting into the helium liquefier, it's coming in already at about minus 160 to minus 170 degrees Celsius. If you had to try and liquefy a gas stream from room temperature, you're going to need an extra couple of megawatts just to get it down to this temperature to begin with. So in summary, it is a very, very energy intensive process. And like with any process, the higher the concentration of helium that you have coming into the plant, the less electricity you use. So really, it is just about trying to optimize and make your plant as efficient as possible to try and cope with the extreme temperatures that you're trying to put all of this together with. In terms of pricing, so there are lots of numbers being bandied about, and by and large, most of these numbers that are being bandied about are all true, but you need to come back to what I was saying earlier in terms of the grade. So if you're talking about balloon grade, so let's call it the 97 to 99.9%, your pricing is not going to be extremely attractive. And that's because typically, most of the time in the world, there's a glut of gaseous helium. So this, depending on where you are, it's a very, very localized product. It can't transport very far. Let me actually just whip out my trusty HP12C, and I will give you an idea of just how much helium you can move in a single trailer. So a single trailer weighs about 26 tons of steel. That's just the steel. There's nothing else in it. That carries 22 normal cubic meters. So 22 normal cubic meters would then convert at about 100 bars of pressure. You don't want to put too much more pressure. It basically moves one trailer of 26 tons will move approximately 350 kilograms of helium, between 350 and 500 kilos. That means that moving your 26 tons, you are not going to be able to move it very far if you're only moving a payload and you're only going to be able to sell 350 kilos of helium. So this is a very, very localized market. Hence pricing over here, last we checked, was somewhere between US $100 to $150 per kilo, maybe more, maybe less, depending on where you are. But then you've also got to factor in an absolutely astronomical transport cost to get it there. Your 4.9s in liquid form starts to get more interesting, but this one cannot be. This one will be used for supercooling and for things of that nature, but it will not be used in a variety of applications. So where you need sterile environments, it's not going to be used. Where you need medical, it's not going to be used. Where you need laboratory grade, it's not going to be used. So this one probably trades at a slight discount to the really expensive stuff. Very difficult to put an exact price on it, but it's a slight discount. Your 5.9 purity is priced somewhere. So if we look at the 2018 BLM auction, that fetched a price in high grade, so in other words 5.9 liquid form, that fetched $286 per MCF. So $286 per MCF in kilogram terms works out to plus minus, call it roughly speaking, $61 per kilo. This assumes that you are taking a container from refinery gate, and that has 11,000 gallons. Of course, now we're also talking about American gallons, not UK gallons. So if you have to try and convert that into any kind of a useful number, then you're talking plus minus 5,000 kilograms into your trailer, give or take. Now there's another issue. You can't actually empty the whole trailer, just because you can't have what's called a hot trailer. So a hot trailer means that it's coming into the refinery, and if your trailer is at a temperature anywhere above minus 190 degrees Celsius, then the trailer needs to be purged and cooled down again. Otherwise, you're going to have a serious problem on your hands when you try to fill it up with a liquid at minus 269. That means that a trailer moves from refinery all the way to its final destination. When it gets there, you can probably only empty out about 4,000, call it 600, maybe a little bit more depending on how long the trip back is. And you have to leave the rest in there to try and keep the trailer in what we call the cold state. So really your transport cost that you need to apply really applies to this volume alone. Give me 1 second. Sorry about that. Okay. With regards to the pricing on this kind of grade, that came in at $286, as I said, at the auction. Typically, helium is sold in very long-term agreements, long-term take or pay. Generally speaking, they're 10-year agreements with a 5-year reopener, and that allows either party to reopen. If they can't reach a mutually agreed price, then you can break the contract. So there's an incentive for both parties to be honest if they decide to price reopen. And then there's all sorts of other funky things like a wild card. I think the early contracts were based off baseball contracts. Believe it or not, it's quite peculiar. There are some baseball clauses in a lot of helium contracts. That's a completely useless fact, but interesting nevertheless. So with regards to where the price is at the moment, if you are buying an entire 11,000 gallon container, then you can expect to achieve anywhere from about 230 to maybe $280/$290 for a long-term contract. And that's per MCF. All of this is per MCF, or as we said, it's just under $60 per kilo. In the spot market, the prices are completely ridiculous. So in the spot market, given the current shortfall, you would be looking at achieving a price anywhere as high as maybe $350, $400, on the very high side, $450 per MCF. This is if you are at refinery level and you are selling an 11,000 gallon container. If you take your 11,000 gallon container and you invest in an inordinate amount of equipment that is going to transfill and keep it liquid and put it into a tiny little dewar, and you sell 1,000 liters at a time, and somehow manage to actually move the liquid helium into that container and keep it liquid without it vaporizing, then this you're going to be selling at somewhere between $1,000 and $1,300 per MCF. Very, very attractive price, very, very complex business model, insanely complex business model. And that involves an inordinate amount of infrastructure. They're called transfill sites. There are a few people that do it. Every yeah, every area will have it. And this is typically the stuff that then goes to hospitals, and the DUA stays there for a couple of weeks while they run their MRIs. So these prices, although they are very attractive, they are not the kind of prices that you're going to get at the refinery gate, because there is a huge amount of infrastructure that is required from the time that you have a helium project putting helium out the ground through to the point where you're selling in a DUA to your customer. That's a terrible DUA, but anyway, I think you get the point. So there's a lot that happens to get from point A to point B over here. So typically the range that you're looking at over here for upstream helium is going to be anywhere from over here, call it $220, $230, $240 up to $260, $270, $280, maybe a little bit higher. In future, that price may be could potentially go a little bit higher, but then we also need to look at the supply dynamics of helium in the long term. So in the short term, there's obviously a crisis. In the medium term, there's Qatar. Qatar is coming online. How do I get this whiteboard off? Give me 1 second. There we go. Stop sharing my screen. There we go. All right, so in the short to medium term, we have Qatar and the first stage of Gazprom coming online. That'll help reduce some of the shortfall. There will still be a shortfall. In the medium to longer term, then obviously you've got more Gazprom elements coming online, and that'll increase supply. And then hopefully by that stage, Renergen's phase 2 project will come online as well. And so the long-term prognosis of helium is that there should be quite a significant amount of stability in the market. But in the shortfall, obviously, everyone is trying to make hay while the sun shines. And yeah, the trick to any good helium project is speed. If you are going to try and participate in the liquid helium market, then you need to know that you need to be able to build a plant really quickly. And the quickest that you can build a liquid helium plant is somewhere in the region of about 2.5 to 3 years, and that's assuming that everything goes bang on track. Yeah, I think putting it in context, we'd been working on our plant for many years before we got to the point where we are now. So there's a very, very long lead time on this equipment. So it's a difficult business, very rewarding, but yeah, it's a very long-term game. So in terms of all of the points that I'm looking at over here, I think I've covered everything. I hope that you found this useful, and that you all now feel that you are adequately trained up heliumologists. And yes, if there are any other questions, feel free to reach out to me. I'm accessible, and yeah, if there are specific topics that you'd like me to talk about, as long as it's information that's in the public domain, I'm more than happy to put another one of these together for you. Thank you for your time, and for those of you that stuck through the entire podcast, well done. I can drone on a bit, so thank you. Take it easy.